It's all the cats.
Hey,
Okay.
Emily.
Yes?
So if we use like a computer software like Desmos has a scientific calculator,
Mm-hmm.
and I use that on my computer. So if I were to write out the equation and then write the answer and then write calculated or something beside it.
Oh yeah, just say calculated using Desmos or something.
Okay.
That's fine.
Okay, cool.
Yeah, cool. Awesome. Um, good. So what I want to do to give you guys a taste of this test is I'll make a practice test and a practice test upload on Gradescope so that you can kind of see what it's going to be like. And then I'll just do, so the Gradescope for the practice test, I'll just do kind of completion marks. It's like, oh, great, you were able to do something. So yeah, so classic situation. I don't have it yet, but I will. Yeah, so do you mean for the practice test, Derwin? Oh, for the actual. So there's going to be a time limit for the WebAssign, and then what I'll do is I'll set the Gradescope to close like an hour later or something, so that you would have time to organize your scans and upload them and stuff like that. Yeah. So there will be a time limit on the Gradescope, as well as the WebAssign, but it would be later. Does that help? Cool. Okay, cool. So I will. You will study, I will do all these things. I will post a practice test on WebAssign and create a practice test Dropbox on Gradescope. And I'll count this as, well, probably 2 assignments, the WebAssign portion and the Gradescope portion. Question? I thought I heard anyways. And they will count as assignments. Okay. So yeah, I want to do that practice test just so, but I want to make sure that you do it too. So that's why I'm counting it as assignments, but should be good for both of us. All right, so let's see here. So we've done 2.1 to 2.4 and 12.1 to 12.3. And then today we're going to do, well, we did 15.1 last day. And then today we'll wrap that up and go into 15.5. Chapter 15 compared to chapter 12 is like, am I missing something or is it actually this easy? It's actually this easy. Yeah. And chapter 2, somewhere in the middle. So what I want to do is, maybe you guys won't like this grade distribution. I was going to do roughly 25 marks for chapter 2, bring it down to 15 marks for chapter 12, remembering that those assignment questions, some of them are really difficult, right? And so I'm not going to make them that difficult on the test, of course, and you'll kind of be able to judge from the practice test that I post, right? It'll be similar. And then from 15, I was going to do roughly 10 marks. I reserve the right to kind of shuffle things around. Oops, 150 marks there, 50 marks. What course is this? CATS 139. So we have about 50 marks, and then there will be additional marks for your written work, right? So as I kind of see fit. Like I said, you'll have a better idea once I post that practice test. Let's see what's going on. Okay. What else did I have written here? Good. I posted homework for 15.1 and 15.5. I think I made it due, now I can't remember, the Friday after, so the 9th, I think, due October 9th. Cool, okay, verified. Obviously, it's due after the test, but because you're being tested on it, then it might be good to go through them. Unlike the last couple of assignments where I would not have given you the menu question, for example, that Little Caesars pizza one. Side note, I posted kind of a blog solution to that one. So I found someone who had gone through that exact same problem, the 12.3 homework, number 19. Yeah. It's really hard. Don't get all done. So there is no inside track at all. Are there 11 toppings? That's what we need to know. Probably more. Yeah, so yeah. So I had to Google it. That was way too hard. I tried a bunch of different ways, didn't work. Anyways, posted the solution. You can have a look there. All right, so like I said, so I went through the chapter 15 homework just to make sure, because I realized that as we're jumping around, sometimes they'll do stuff that we haven't covered yet. So just a couple of notes for homework 15.5, numbers 7 and 8, I think it is. It gives you like a plotting window, making you think that that's the, like it gives you the X min, X max, Y min, Y max. You'll see it when you get there, but for now, just kind of make note of it. Just ignore the plotting window and just look at the graph for the domain and range. Ignore plotting window. Just look at graph. Cryptic. For domain and range. I'm only squeezing it in because I only have one more line before the page break. And then for number 9, I would say use Desmos, because we haven't actually talked about how these graphs behave. that would have been covered in an earlier chapter that we're not doing. So anyways, just use Desmos to graph it and pick the right graph. All right. Any questions before we start with today?
Sorry, Emily, what do you mean by used Desmos?
So question 9 is going to be like, pick the graph of this function. So then it gives you a bunch of different options. So I would just use Desmos. Have you guys seen Desmos before? Have you used Desmos before? So Desmos is a free app. Where is it on here? Here. Well, I don't have a pointer, but it's the green one with the lines. Whee! And it's just a free app. You don't even need to make an account or anything. You can just kind of 4x squared looks like this. You can kind of zoom out, and what else can you do? Move the dot. I think you can move the dot. Oh, 0, 0. Oh yeah, there. Anyways, it can do a bunch of cool stuff. So yeah, so, and yeah, I think you can just go to desmos.com and it'll have it there. So, or you can install it or get the app. There's an app for that. Okay. So Desmos is really, really useful, especially for graphing stuff. Make sure you put in your function right though. Otherwise, what a mess. Okay. Any other questions? Oh. All right. Let's do a little bit of sort of review. We talked about the Cartesian coordinate system. Well, I mean, first we finished off chapter 12, but I'm pretending it never happened. So we talked about the Cartesian coordinate system. We brushed up on some terminology, the XY axes, the origin, the ordered pairs for a point, right? And so just kind of terminology like that. We talked about the standard form of a line. Which is ax plus by plus c equals 0. Then we talked about the more kind of familiar form of a line, which is the slope-intercept form of a line. Slope-intercept form of a line, which is essentially y equals mx plus b, or some version of that. We also talked about the slope, so kind of components of the slope, and we said the slope m, right? Remember in the slope-intercept form, m is the slope and b is the y-intercept, right? And so, and then we said the slope, if we have a line going through x1, y1, and x2, y2, then the slope would be y2 minus y1 over x2 minus x1. And we also talked about positive and negative slopes. So we're going to keep talking about slopes a little bit. Slopes, hit the slopes. Specifically, what it means for two lines to be parallel, but also perpendicular. Parallel, right, you've got something like this, and then perpendicular is when you've got a 90-degree angle between the two lines. So, but what does that mean in terms of the slopes? Well, parallel is easy. So two slopes how did I want to say it? Can't just jump right in there. Ah, maybe I can. Without abandon. Two non-vertical lines. Two non-vertical lines are parallel. Non-vertical meaning they can't be like this, which we'll see later. Well, that actually has a bit of a slope, actually a lot of slope. If I was able to draw, so they can't be like this. Come on, straighten out. Doesn't want to. Hey, this program is supposed to, yeah, correct all my lines. It doesn't want to do or it wants to only do non-vertical lines. Anyways, I think you get the idea. Vertical line, non-vertical line. Yeah. Yeah, we'll say that vertical line has no slope, but technically it'd be infinity. Well, rise over run, you don't have any run. It doesn't matter, we're gonna say no slope. I know, division by zero, illegal math. Two non-vertical lines are parallel if and only if. Are you guys okay with IFF, if and only if? Well, you will be. If with two F's is if and only if. They have the same slope, which you probably figured just from kind of general knowledge. So that's if two lines are parallel. Harder, or a little bit harder, is to determine if they're perpendicular. Okay. So two lines with slopes M1 and M2, oops, that should look like a 2, not a, I don't know what that was, are perpendicular if and only if M1 times M2 equals -1. Okay. So this would be the same as saying that, well, I could rewrite it as M2 would be -1 over M1. Okay. So a little bit harder, but not hard, to figure out if two lines are perpendicular, right? You'd have the slope of one, you'd have the slope of the other. If you multiply them and they equal -1, then they're perpendicular, right? Perpendicular, looking kind of like, wee, 90-degree angle. Hopefully you're okay with the angles. And then of course, parallel, looking like that. We could also have a horizontal line could be perpendicular with a vertical line, right? So also a horizontal line which has slope 0, right? So if it's something like this, then you have no rise, but you do have some run. So 0 divided by anything is 0. So a horizontal line, slope 0, is perpendicular to a vertical line, which we say has no slope. Okay. So, any questions about that? Slope 0 does not equal no slope, correct. So a slope of 0 means like this. So here, for this one, m is 0, and this one has no slope. Yeah, so if they're perpendicular, well, I mean, by definition, perpendicular is if m1 and times m2 equals -1, right? And so, and that will be at some point, but we don't have to specify the point. All right, let's draw some lines. Oh yeah, boy. So there are kind of two common ways that we can draw lines. And it seems pretty basic, or like a basic thing to have to be able to do, but it is really important to be able to draw a straight line. So the key is that you need two points on this line, which we saw last day was the solutions, right? The solutions to a function. Yeah, so you could also say that the slope for m2 is the negative inverse of m1. That's correct. That one there. Good. Oh yeah, so to draw any straight line, you need to have 2 points on that line, and then you need to take a straight edge, and usually I just cheat and I take my, if we're doing like a paper thing, then I would just put my 2 points on here, and then I'd kind of bend over my paper as a straight edge, connect the dots, extend the line, and there you have it, right? But the idea stays the same. You need 2 points, or at least 2 points on the line. Sometimes it's nice to have 3 just to double check. But we put 2 points that should be on the line, and then you take any sort of straight edge, get creative, and you connect the dots, and then you extend the line, and that's it. Right? So, but there are kind of 2 different ways that we could find those points on the line. Oops, wrong color, devastating, no. There are 2 common ways to draw a line. You'll see that they both use the same kind of idea. One is by plotting points. Which is find 2 points on the line. So this is the one I was talking about, right? Find 2 points. Find 2 points on the line, right? We could also say find 2 solutions. connect the points with a straight edge. With a straight edge and extend the line. So then the other option is if you have a point and the slope, then you can draw that point and then use the slope to kind of Tetris your way over to where you want to go. So given a point and the slope, which would mean, okay, we're going to plot the point. And then plot a second point. Plot a second point by moving the slope amount. So here are some things that and then I guess we should finish this one. I'm gonna steal this. Then you have 2 points, right? The one you first had and the second point that you got while moving around the slope. And then of course you connect those 2 points with a straight edge and then you extend the line. So I'm just gonna copy this here, paste. Change it to C and be done with it. Cheating. When we talk about kind of moving the slope amount, there are some things that we self-plagiarism. Yeah. So there are some things that we need to keep in mind, right? When we're on this kind of grid system here, right? If we've got, I feel like we talked about this last day. Yeah, if we've got the grid system, let's just remember. All right, this would be in the positive direction. X, Y, this is the positive direction. This is the negative direction of X. So once you pass the origin, you're moving in the negative direction, of course. And same thing for the Y. And this is going to be reflected in your slope, right? So let's do an example. Or a couple of examples. If I want you to graph y equals 2x plus 2, you could do it either way. The easiest way here is to find 2 solutions because you have the line, the equation of the line, and not just the point and the slope. So you can use this equation for the line to find solutions and then plot those solutions. And so what we're going to do here is we're going to find 2 solutions. Might be nice to have more than 2, but you only need 2 points. So here, what we do is we pick kind of convenient values of x that you feel like plugging into this formula. Obviously, this one's nice and easy, but we can pick any value of x. I would add convenient. It doesn't have to be, but why wouldn't it be? So if I set up this kind of table here, if x is my go-to 0, then y equals 2x plus 2. If x is 0, then y would be 2. Okay. So now, the first point that I have is at 0, 2, right? Because for ordered pairs, we list them as x comma y, right? So when x is 0, y is 2. For my second point, let's do, let's be lazy. How about x is 1? X is 1, y is 2 times 1, which is 2 plus 2, which is 4. Making the second point here 1, 4. So what I'm going to do is make this amateur style graph. So kind of usually I'll have my x with an arrow here and y with an arrow here. If you want to be proper, you can put arrows on all 4 sides. I get lazy sometimes and I only put them here, but that's okay. And then of course, I'm gonna just set up my quick sketch grid. So 1, 2, 3. 1, 2, 3, 4, 5. Ish. So then my first point was 0, 2. So when x is 0, y is 2. So this is 0, 2. Then I'll use a different color. How about for 1, 4? So when x is 1, y is 4. This is obviously not very beautiful, but there we go. And then our line, what we do, right now we have 2 points. We would take a straight edge. I'll use this pen, I guess. Try to see how it goes. I connect the 2 dots, and then I extend the line. It worked pretty well. And that's it. You could put little arrows here if you want to, but you don't have to. I'll often omit them. So that's usually if you have the equation or if you have the line, then you can just find 2 solutions on there, find those on the graph, plot them, be done. Another example would be graph the line. Graph the line passing through -6, 1 with slope m equals -2 over 5. Okay. So this is one of those situations where you have a point and the slope. So you could go ahead and you could construct your equation and get it to look something like this. But it might be easier to just plot the point that you've been given and then move the slope amount around your graph to figure out your next point. So let's see, let me graph my, move it here in the middle maybe. Should have counted how many I needed. Anyways, we'll see. things got kind of spacey there, but especially on the y-axis. Woo! Okay, that's all right. So first thing I'm going to do is I'm going to plot my -6, 1 point. So I'm going to go to 1, 2, 3, 4, 5, 6 in the negative direction, right? So here's -6, and then up 1, which puts me at -6, 1 here. Okay. Now, to move my slope, right, one of these is going to have to be negative, right? So one thing to notice m could be 2 over -5. Right, so that negative could be on either one, but only on one, right? So it can either be on the rise or the run, right? But it can only be on one of them to make it negative, right? So if we have a look at it like it is, -2 is our rise, which means we would go down 2, right? Let's see here. 1, 2 to -1. So run equals -2. That's kind of a halfway there point, right? So that's why I'm just not really drawing it in. Oh. Rise. The rise is -2. So basically a drop of 2. And the run, which I was saying, but erroneously, is +5, which means I have to move in the positive direction. And so then I'm going to go 1, 2, 3, 4, 5, putting me at -1. Right? Maybe I should do arrows down instead. Down and over. Down 2 and over +5. So now I have 2 points, right? Or if I go for this option here, right? If I move up 2 and then to the left 5, right? Let's try that. So if I go up 2 from here, 1, 2, puts me at 3. So, oh. Rise is 2. And then to the left 5. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 6, 7, 8, 9, 10, 11. And join these up. Oops. There. With a run of -5. If my graph had been better, these would all be on the same line, right? So it doesn't matter which way you go, but as long as you only treat one as negative. So then here, I need a longer straight edge this time, so I'll use my calculator. And hey, not bad. Sort of. I'll try again. Hard to catch them all. Sort of. Okay. Okay. Good. Any questions about that one? So kind of two ways you could do it, or we can combine them and say, well, what if we have something like, if we want to graph the line x plus 2y equals 6. Okay. So you have a couple of options, right? You could rearrange and solve for y. That's totally reasonable, right? And I'd say it's probably the easiest way. And then you could find solutions, or you could, right, if you rearrange it into y equals mx plus b, you could have the slope, and you could use the easy intercept. If you prefer this method of drawing a line, I actually prefer the first method. You just solve it, figure out 2 points on the line, plot them, be done with it. Right. So what we can do is we can graph. Well, we can't graph it. We can use several approaches. That's what I meant to say. The graph is all the same. We can use several approaches. I will solve for y. To find the equation of the line in slope-intercept form. So we've got x plus 2y equals 6. Essentially, I'm just solving for y here, right? And so moving everything else over, I get 2y is 6 minus x. So y must be 6 minus x divided by 2. I can split up this, this fraction, right? Making sure that 6 is divided by 2 as well as x is divided by 2. So I can rewrite this as y equals 6 over 2 minus x over 2. So y is going to be 3 minus, and then if we want to have it in the same form, mx plus b, or in this case, b minus mx, but or b plus mx, you could write 3 minus 1/2 x. So now the y-intercept is at 0, 3, right? The y-intercept by definition is where it crosses the y-axis, so that's where x is 0. And the slope is negative 1/2. Right? So notice that you have a point that's on the line and you have the slope. So we could use this tactic. Catching up, okay. Right, we could use this tactic where we plot a point and then we use the slope to move over. Right? Or we could just use our y equals mx plus b to find solutions. Right? It is up to you. Let's see here. I will use the equation to find two solutions or 2 points on the line. I will use the equation to find 2 points on the line. That's because it's my preferred way. Because then I can set up my x and my y. Y equals 3 minus 1/2 x. If I let x be 0, that's easy. And I already did it. Then I get 3, which means I have a point at 0, 3. And if I now we want to pick convenient values of x, right? So if I let x be 2, right, instead of 1, 1's kind of tricky because then it's minus 1/2. If I let x be 2, then I get 1/2 times 2, which is just going to be 1, right? So then I'm at 3 minus 1. So you want to be kind of sneaky about what values of x you're plugging in there, because then y is going to be 3 minus 1, which is 2. So 2, 2. And then super rough sketch here. Zero, 3, let's say is here. And 2, 2, let's put it here. Take my straight edge. Didn't even catch it. I guess I'll try again. Good enough. Okay. Yeah, you just gotta like really blow up your points. In case the line's not doing what you want it to do and you've already committed, just make your points bigger. Totally. Oh yeah, so drawing lines, pretty fun. I dare say pretty easy. Right, so just practice. One thing to note that we already talked about, right? If we have a horizontal line, then the slope is 0, right? And if we have a vertical line, then we have no slope, which we already talked about, but I do want to put it here officially. So note, if a slope is 0, we have a horizontal line which would look like boop, boop, something like this, m equals 0. And if the line is vertical, there is no slope because we can't divide by 0. That line can still exist though. But it's this perfectly straight vertical line. Not mine, but let's say it's at y equals 2 and here, or sorry, jumped it around. Y equals 2, and let's say that this is at x equals 2, for example. It still works, But you have no slope. Okay. Any questions before we start 15.5? Start on a fresh page here. .5 is really just introducing functions, and then after the test we're going to talk about kind of one-to-one and onto functions, as well as the inverse and the composition of functions. So we will talk more about functions, but for the test we're going to just do this section and then test on it, so it should be pretty fun. But a function is probably something you've seen in math. Pretty fun. Functions you've probably seen before, right? I don't know. I think it's one of those things that you should know what functions are, but sometimes they can be kind of hard to think about. So it's good to introduce them again. A function, let's just start with a little definition here. So many definitions. A function is a set of ordered pairs, essentially an input and an output, right? Where the input can only be associated with one output. It doesn't have to be the other way around, right? But one input can only give you one unique output, right? You can have multiple inputs going to the same output, which we'll see, but a function is a set of ordered pairs and I'll do kind of input, output here as my ordered pairs, in which the first component is associated with exactly one second component. With exactly one second component. The dog falls asleep to the drone of my voice, so she didn't even notice that the door opened. Now she's feeling foolish. The exactly 1 second component, cats or dogs? She's a dog. She's a little dog. Well, she acts like a cat though, so. Oh yeah, so the key is that you can have multiple inputs go to the same output, but not vice versa, right? And so here, in which the first component is associated with exactly 1 second component, right? So what does that look like in terms of, so if I have, typically we go from an input here, input to an output, I think. which means that I can have an input here, and it can go to one output here. Okay. What I can't have happen is, so this would be a function. Everything going to one output. Okay. In fact, you can have something go to the same output. That's fine. But as long as from here, there's only, so from each element in the input, you can only have one mapping, right? They can map to the same thing, that's allowed, right? So this would be, this is a function, and I'll scoot this over, and I'll draw, well, you hate to use green. Green means go. Here, red. Oh, that's nasty. Not a function would have, so just kind of recreating here, input, output. If I go from one input to two potential outputs, that's not a function. So let's have a look at an example of this. Which of the following sets of ordered pairs are functions? So we'll have a look at 0, 0, 1, 2. 2 goes to 4, 3 goes to 9, and 4 goes to 16. We're not talking about what the function is that does this quite yet, right? So even though you might be able to see it here, again, we've got 0, 0, which is the origin. 1 goes to 1, 1 goes to -1, 4 goes to 2, and 3 goes to -2. Whoa, what the heck? 3 goes to -2. Or option C, 1 goes to 3, 2 goes to 3, 3 goes to 3, and 4 goes to 3. And finally, option D, 3, 1, 3, 2, 3, 3, and 3, 4. It does help if you read them as 0 goes to 0, 1 goes to 2, 2 goes to 4, 3 goes to 9, and 4 goes to 16, or you could even map them out like we did like here, right? And just make sure that they don't go to the same, or you have two lines from the same input. That's not allowed, right? And so here, 0 goes to 0. There's no other mention of 0 going anywhere else in this line, right? So that's safe. So 1 goes to 2, okay, fine. 2 goes to 4, fine. 3 goes to 9, 4 goes to 16. We've got these individual inputs and they happen to produce individual outputs. Okay, so this is a function. Green means go. A function. What about the next one? So 0 goes to 0, that's fine. 1 goes to 1, okay. But then we have 1 goes to -1. So that's a problem because +1 from the input can give me either 1 or -1, right? There are things that exist that make this happen, but it's not a function, right? And then 4 goes to 2 and 3 goes to -2, but because we already decided, not a function. And those two are the culprit. Okay. In the next one, 1 goes to 3, 2 goes to 3, 3 goes to 3, and 4 goes to 3. So that's a really funny background now. Be right back. Here, right, at first we kind of get jolted because, or at least when you look at this, I would say, okay, well, they're all going to 3, so I have to stop and think, well, as long as the inputs are all unique, then I'm allowed to do that. So this is still a function where we're going to, right, we're allowed to have different inputs go to the same output, right? We just can't have the same input yield different outputs, right? So that's the distinct difference between function and not a function. So this is a function. So have a look at the last one. So 3 goes to 1, 3 goes to 2, 3 goes to 3, and 3 goes to 4. That's a no-go for me, right? Because from 3, I've got 4 branches, and that's not a function. Because all of these are the culprit. Not a function. Oh, about so if you've dealt with functions, you probably have heard, you know, functions are this machine and you put in some input and it gives you some output, and yeah, we're going to keep doing that. We're going to keep talking about it as like a machine, but not for very long. But it is a good practice, especially, so I saw on the assignment, so there are a couple of word problems where you have to read what the machine does, and then it'll, like, you have to construct the function. So I think that's a good exercise, just to kind of go both ways. Because we can often read a function, a mathematical function, and explain what it does, but going the other way is a little bit trickier. So you can give those a try on the assignment. We can think of a function as a machine. That takes input and returns an output. I guess it's an input. And returns an output. So we're going to use functional notation. So we will use The textbook called it functional notation, which is kind of fun. I would just call it function notation. So functional slash function notation slash funky notation. It's not called that, but if it helps. F of x, right? So this you're gonna read as f of x. Whenever you have something kind of pushed up against some brackets, usually the brackets, the start of them, you would read as of, right? So P of t, Q of 4, that kind of thing, right? And so you would read as kind of whatever the name of it is, and then of whatever is on the inside. P of t, Q of 4. So here, this is the name of the machine. Name of the machine. I'll put it in quotes. So many quotes on this little page here. Oh, I guess I should use a different color. And these are the inputs. But each of them only have one, so I'll keep it singular. So in f of x, which is kind of our typical setup, right? F is the machine, right? X is the input, just to summarize. And then finally, f of x itself is the output. And f of x as a whole thing is the output. Oops. We move on to the domain and the range. If you have heard about the codomain, we'll leave it for a little bit in case we ever need it, but usually we only talk about the domain and range. So the set of all possible values of x is the domain. While the set of all output values, for f of x is called the range. The domain and the range. Right? So the domain is all the possible input values, so all the values of x, and then of course the range is all the possible output values, or all the values of y, if you want to think of it that way. So we have, it wasn't, I guess it was like in high school maybe, where it clicked and I was like, hey, f of x and y, they're the same. WTF. Right, and so it wasn't until I realized that you're able to kind of interchange those, and of course it's one of those things that, you know, your math teachers tell you, but until I realized that you can use f of x and y interchangeably, there was kind of that disconnect. So I'll put it as a note here. So it is common to use f of x and y interchangeably, right? Or in notation, we can say f of x equals y. Because then when we're talking about the output values, really what we're talking about is all the possible y values, right? Domain, range. So that's just kind of a note. It's not even an LFF, it's just an F, a fact. How about a little example? If we let the function g be a machine, I don't know why I don't like calling it a machine. I guess it never really, I don't know, it didn't click with me. So capital F of x versus lowercase f of x, there's no real difference except the name of the machine, right? So capital F of x, we could have something like capital F of x is 2x plus 1, whereas lowercase f of x is 40x plus 3, right? So they take the same input, but they definitely produce different outputs. And so that's what we mean by the machine, right? So here, this is just the name of the machine. And often we'll have multiple. I was just saying I didn't like saying machine, and now I'm using it. Okay. This is the name of the function, right? So the name of the machine. All right. Here's our example. So let the function g be a machine that takes a value. So let the function g, right? So now the name of our machine or our function is lowercase g. Be a machine that takes a value, adds 2, then multiplies by 5. What I want us to do is I want us to write the general function. And I'll leave a little bit of space there. And then well, I guess we should do that first, because then I use the notation just as in a little bit here. So I'll go for the light blue. So if we have g, well, g is the name of this function machine. So G, it takes a value, it doesn't specify what we should call that value. And so G of X, let's call it X. It's gonna take a value, so I'm gonna start with an X here, and then it adds 2 to that X. So X plus 2, and then multiplies by 5, right? But that 2 has already been added onto the X, of course, and so I have to put brackets around X plus 2, and then times 5, right? Or we can rewrite this as G of X is 5 times X plus 2. Just looks a little bit nicer to have that 5 on the left-hand side, and then use the brackets for the multiplier. Oh. So now I want you to use that function to find G of 4, G of -3, and G of pi in exact notation or exact form. Because it takes a value and then it adds 2. So we have to have that adding 2 and then multiply by 5. Good. So G of 4 is going to be, oh, I guess I've been using the light blue. G of 4, we can plug it in as 4 plus 2, or I guess I rewrote it. 5 times 4 plus 2. Brackets first, right? BEDMAS. So 4 plus 2 puts me at 6 times 5 is 30. G of -3 is 5 times -3 plus 2. I have to deal with the brackets first. -3 plus 2, -1 times 5, -5. And then G of pi is 5 times pi plus 2. And this is the exact solution, right? So here, exact solution. Usually we don't use the approximation of pi that your calculator gives you, right? We would just use pi as a variable, or not a variable, as a constant, or the constant that it is. All right, so this is the exact solution. You could expand it and say 5 pi plus 10, but that's the same thing, right? So there you have it. If you were having a hard time with part A, one thing that you could have done is you can work through some of these typical scenarios, right? And try to see, okay, well, if I have G of 4, I have to add 2 and then I have to multiply by 5, just using the verbal description. And then see what you would have to do, right, mathematically in order to get there. And then you could work backwards from here to get that general function, right? So sometimes it's easier to work that way than to just develop the function. This one was kind of breezy enough, but sometimes it's easier. Okay, so there's this thing called the difference quotient, which we use in calculus a lot, but it's just a good exercise in working with functions. And so the difference quotient is used in calculus but we will use it as an exercise with functions. And the reason I want to kind of work on it is, well, one, you'll probably end up taking calculus at some point, even if you don't want to. I don't think you have to, but I don't know, it happens to the best of us. And then two, it's just kind of a tricky thing to master is the difference quotient. So the difference quotient is f of x plus h minus f of x divided by h. Okay. Looks reasonable enough, right? The idea being, okay, you take x plus h as your input, and then you take your x as your input, and then depending on the function, you'll be able to simplify, and usually the h cancels out. So we'll try it with a function, and you'll see what I mean, because it throws people off that you'd have to find the function or evaluate the function at x plus h, and then subtract the function evaluated just at x, right? And then divide it all by h. So it might be easiest to just figure out what f of x is on its own, figure out what f of x plus h is on its own, and then kind of build it up after that. So for example, if f of x is 1 over 2x squared, find the difference quotient. Oh. Let's see. So I want you to give it a little try. So I just made a little note here while I was letting you guys work on it. So it can be helpful, like I said, to construct the individual components of f of x and f of x plus h before finding the difference quotient, just because it's easier to miss parts if you're doing it all at once. Now, as you get better at these, you will probably just start building this whole thing up immediately, but for now, let's start by finding f of x. Well, f of x was given right? It's 1/2 x squared, which we could rewrite as x squared over 2 if we want. So it's 1/2 x squared or x squared divided by 2. Those are the same, of course. So that's fine, right? The tricky part is going to be f of x plus h. So now wherever you see an x in the function, you want to put in an x plus h instead as one thing. So this is going to be 1/2 x plus h squared. Okay. So the x is being replaced by x plus h in brackets. Okay. So we can expand this, right? X plus h squared is x plus h times x plus h. So let's see here. 1/2 times x plus h times x plus h. And I always expand slowly. Some people are really good at expanding, right? And so, but I just go x times x, x times h times x, h times h. I do them all. But if you're really good at expanding, then good for you. So x squared plus xh plus, and then I will tweak it so h times x is the same as xh. So I will rewrite it immediately, xh plus h squared. Right. You don't want to be doing any legal math where you just pull the square in because you're adding here, so you're not allowed to do that, right? If you're adding or subtracting inside, you have to expand it. If you're multiplying or dividing, you're allowed to just bring it in, but only if you're multiplying or dividing. So this becomes 1/2 times x squared plus 2xh plus h squared. Okay. I don't think I can simplify this anymore, really. So what I'm gonna do, I could bring in that 1/2, I guess. Sure, let's do it. 1/2 x squared plus 2xh, mix up my notation. 1/2 x squared and then 2xh over 2. They're the same. I know, bad. Actually, not that bad. Plus h squared over 2. Here, because I'm multiplying 2xh and then dividing by 2, that means I can cancel, right? So I don't think there's any more that I can simplify here. So now I'm going to be able to start making my difference quotient. So my difference quotient is f of x plus h minus f of x all over h, which in this case, well, this here is my f of x plus h, and then my f of x, we'll use the same kind of writing style, x squared over 2, and see what happens. I like to use brackets to kind of show that, hey, here's f of x plus h, and here's f of x. And so I'm going to use square brackets, x squared over 2 plus xh, because I canceled those two. You could have kept those twos for a little bit longer if you wanted, plus h squared over 2. Minus x squared over 2. So this here is my f of x, plus h. And this is my f of x. And then don't forget, it's all over h. It's all over. Yeah. Because I'm not multiplying anything, These brackets are just decorative, right? And so I can ignore them and I can take x squared over 2 minus x squared over 2 and be done with those two terms. So I can cancel this and this. And let's rewrite what we have. So that means that we have xh plus h squared over 2 over h. I can pull out a common h, and like I said, if you don't end up canceling the h in the denominator, you've done something wrong. So this will kind of always happen where the h will cancel with each of the terms. So if you find yourself where this term doesn't cancel or something like that, then something went wrong, right? So what you're left with once things have canceled out are just terms with h in the numerator, so that you're able to pull out a common h and then cancel them. So what we have is we have h times x plus h over 2 over h. And because I'm multiplying h by something over h, again, I'm able to cancel those guys. Bink, bink. So then my difference quotient is going to be x plus h over 2. So we don't use it any further. Hey, when does the fun start? That is fun. Difference quotients? Come on. That is true. The fun starts when you let h approach 0, Michael says, and that is so true. Yeah, find the limit as h goes to 0. Good. How about the vertical line test? That's better. How to determine if it's a function just using the graph. So the graph of a function, so here that's the end of that. The graph of a function must pass the vertical line test in order to be considered a function. Considered. So the vertical line test, just says that every vertical line I see Ashley died and came back. That's how fun the difference quotient was. So every vertical line passes through only one point on a graph, right? So every vertical line passes through the graph of a function in at most one point. So I've got a couple of examples here. which I'll draw out. Use the vertical line test. Oops, it doesn't really read vertical. Use the vertical line test to determine if the given curve, so there can be curves that are not functions, and that's okay. If the given curve is the graph of a function, is the graph of a function. I also want to talk about the probable domain and range. So not exactly, but kind of what it looks like, because I'm just doing quick sketches. Also give the probable, the probable domain and range. So for the first one, I've got my XY axes here, and let's see here. Actually, something like that. Maybe I'll scoot it over. Hey, what am I doing? I can just copy pasta here. In fact, that's good. And I would keep it on one page. This one is going to look like parabola, but the other way. Let's do this one like this. Oops. I know, right? Circles. Ovals. All right, so the vertical line test, right, to check to see if we even have a function, says that every vertical line passes through the graph of a function in at most one point, right? So it's just circles out of nowhere. So here, if I draw vertical lines along here, it looks to me like if this function keeps behaving, hey, I said it, the way that it looks like it's doing, then this would be a function, right? Because I'm only crossing the graph at one point. Okay. So this passes the vertical line test. BLT, anyone? Now we're all hungry. Therefore, is a function. All right, let's go to the next one. We'll leave the domain and range for a little bit. The next one, right, again, ding, 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 ding. I'm only passing through bacon, lettuce, and tomato. Yeah. Weird, I can't think of a single thing that starts with V that you'd put on a sandwich. Vegan bacon. Veggies? Oh, venison. Vegemite. Vegemite. Vodka. Just a soaked sandwich. How about this next one, this third one? Yeah, bad day. Have a vodka soaked sandwich. Gross. So here, this is our first example where it doesn't pass the vertical line test because it crosses the graph at more than one point, right? So, nice touch with the white bread. Is a function. Nope. I got carried away. It is not a function. Pay attention. What meal cares? How about this next one? Looks pretty good because I didn't draw it very well, but these keep extending a little bit off to positive infinity and negative infinity. So here, this is a function, and I mean it this time, not like last time. Here, I only have to draw one line to see that on a circle or on an oval, that's no longer a function, right? So here, this is not a function. They still exist, right? But we can't call them functions per se. And here, if I draw a vertical line, pretend it's all over the one vertical line that exists, right? Well, then it's passing through every single point on this line, so this is not a function. And I've totally gone over time, and I'm sorry. We'll do the domain and ranges, or the probable domains and ranges at the start of next day. How about? Any questions before I let you go? My apologies for going over. Can you go, yeah, there? Oh yeah, the pizza solution is on Moodle. I posted just the link on Moodle. I hate difference quotients. Well, once you tame them, cue Tiger King background. All right, I'll let you guys go. We should all get t-shirts. I trust Michael. All right, I guess I should stop the recording. Anyways, bye guys. Oh, awesome. I'll pull through.